Thanks everyone for joining us today for our water talk titled Adapting Water Distribution System Models for Surge Analysis Using InfoSurge. I am Yusuf Al-Fahim, a solutions engineer with Autodesk, and with me today is Crystal from Hazen and Sawyer. So Crystal, if you can give us a little bit of background about you.
Hi, I'm with Hazen Sawyer. I've been with Hazen for about 21 years. Did not start out as a hydraulic modeler, but became one over the years and been doing about Transient now for about, I would say, 16 to 18 years of my modeling. And look forward to just sharing some insights I've had and the benefits of utilizing InfoWater's product. So.
Yeah. And we're very happy to have Crystal with us today because she has a ton of experience with Transient. So this is going to be a great opportunity for her to knowledge share with us. And speaking of knowledge sharing, really one of the key characteristics that we're trying to get out of these water talks is just building this sense of community for all attendees. And so there's going to be a chat box and a Q&A box in this Zoom meeting. What we would ask is if you have any questions, please make sure that you go in the Q&A box. If you want to discuss things amongst yourselves or between folks, you can put that in the chat box, but we're only going to be answering questions in the Q&A box. So we're not going to be answering questions in the chat box. And an additional note that I wanted to point out is that we have 3 upcoming webinars. One, end of September, is going to be on Info360 Insight and Asset. And then there's going to be 2 webinars, 2 water talks in October. The first one in October 4th is going to cover InfoWorks ICM. And then later on October 18th, we're going to be discussing pump and system curves in InfoWater Pro. And that is all I have before I pass it on to Crystal. So here we go, Crystal, you can go with it.
Thank you. So today we wanted to talk about adapting water distribution system models for surge analysis using InfoSurge and InfoSurge Pro. So just going to give you a brief background on surge, what we mean by that, and present a couple of case studies, 3 case studies actually, of using full distribution modeling to assist our clients in coming up with some mitigation devices for their problems. So what is surge? Surge is just a fluctuation in flow or in pressure that often happens suddenly. I like to remind people, and you may have read this in literature, that for every 1 foot per second instantaneous change in velocity, you will see a rise of 50 to 60 psi. That rise will be on the suction side of whatever's causing your transient, or a drop in pressure on the discharge side. So things that could cause that transient is could be done by a pump, just normal operation of the pump starting or stopping, or it could also be done with a sudden power loss at your pumps. It could be done with a valve downstream of a reservoir or upstream of a water treatment plant process. Suddenly closing can also generate that upstream pressure or the downstream pressure. We've also noticed that air valves, if they are not sized properly, can also suddenly close and generate its own transient. You have also just rapid flow changes from a pipe break or fire hydrant operations. We've also seen instantaneous demand changes from customers, whether it be just a customer that has their own storage tank they're filling up, or we had an interesting example of a client who had a lot of large washing machines that would just turn on and turn off, and that would generate transient pressures in the system. So in the past, we often looked at really simple hand calculations. The Drowowski equation comes to mind, and this is a picture of Mr. Drowowski. And manufacturer representatives have also assisted engineers with sizing surge relief valves. But the important thing is that transients are really dynamic and require more than just figuring out what the max pressure was. We do have a lot of concerns about low pressures, and that's becoming more evident in the research, and also just in what I've seen just with our clients. Low pressures can have potential health contamination. You could start, pipes were designed for outward pressure, not inward pressure. So negative pressures can start allowing stuff to come into the pipe that wasn't meant to be. You also have vapor cavities. If they collapse, they become instantaneous, and it also create very severe pressure spikes. Oftentimes, not all the modeling software can pick up those instantaneous pressure spikes from a vapor cavity collapse. So we just try to solve for those issues if we see them in our modeling. Transient cycling is also an issue. If you have a lot of PVC pipe, you got the pipe fatigue. And so modeling allows us to understand that cyclic behavior just from normal operation. So Surge model allows us to understand the dynamics of the entire system. And it can also help you to do what if scenarios without actually going in the field and trying things and preventing yourself from doing damage. So these are some of the papers that I've read through over the years. This talks about the importance of actually using the full model if you have it available to understand your system. A lot of times our customers or our clients just have pressure gauges at their treatment plants or at their booster pump stations, but that doesn't necessarily tell them what's happening out in their distribution system. And so having a full scale model allows us to do that. Again, I'll just read the titles: the potential for health risk from intrusion of contaminants into distribution system from pressure transients. Again, talks about hydraulic transient guidelines for detecting water distribution systems. And also one was this one here, the need for comprehensive transient analysis, talks about how the dead end influences. So we will actually see this, that the pressures will go out into the distribution systems, and when they reach the dead ends, it can have a huge impact on what's happening in the pressures and the transients as it migrates back towards your pump stations. And then again, another article talked about contamination intrusion through leaks in the distribution system.
And this is really the why, right? Why care about transients?
Right. This is why we want to do that. Right. I did want to step back and just talk about hydraulic modeling, what the difference is. So in a hydraulic model, a lot of times these full distribution system models are built from the GIS. We've improved our GIS extensively. I remember when I first started doing modeling, GIS was just relatively still new, and a lot of our clients had a lot of things that were just still in AutoCAD form or on paper form. And so we were building models off of that. Now we can build them directly from GIS. The models have a lot of good information that comes from our billing data, our plant production, includes the pipe data we need, the pump curves, the tank data to do the basic hydraulics, right? So, if we're at a node, whatever demand, comes in from the pipes have to equal each other, right? You got that loss balance going on, as well as the model helps us identify the head conditions and the pressures. Again, the Hardy cross stuff, but the model does it for us, so we don't have to do all that work anymore. And we calibrate the models, so we make sure that the hydraulic models match what we're seeing in the distribution system in the real world based off of operations of the pump stations and the treatment plants and the tanks and the valves that they have going on. Now, when we get into transient, there's two right now main kind of methods that they have to kind of solve transients. So one is called the method of characteristics, the MOC, and the other one is the wave characteristic method. And so you have the Eulerian, which is the MOC, and then the Lagrangian method. And so the Eulerian, it uses a lot of partial differential equations. It updates the hydraulic state of the system in a kind of a fixed grid system as time advances in a uniform increments. It takes numerous steps to solve transient pipe flow. So for very complex, large water distribution systems, it will take a very long time to run. It requires calculations not just at the nodes, but at all pipes, interior points inside the pipes. And a couple of softwares that do this is Bentley Hammer and AFT Impulse. Whereas the WCM, it solves transient flow equations in an event-oriented system simulated environment. In other words, it has a method to track the movement and the transformation of pressures as they propagate through the system and computes the new conditions at fixed time intervals or when there's actually a change that occurs. So there's fewer pressure and flow calculations, and more complex systems will run in a shorter period of time, and because it's only doing the calculations at the nodes and at the pipes. And right now, this is seen in KY pipe, and KY pipe actually is not 2018 anymore; it's like 2022 Surge. And also in Pro, InfoSurge Pro. So this is just kind of like the mathematics that goes into MOC. I don't know if a lot of you paid attention to differentials class, but this is it. This is where differentials come in, and partial differentials, and it's very convoluted at times. It gets the job done, but it takes a lot of effort. Whereas the WCM method is very simple calculation. And the reason it works, again, is because it does rely on the sonic pressure, which is the wave speeds. So you got the wave speeds, you got the pressure, you got the velocity, and it is doing differentials, but it's only doing it at the nodes and the junctions and at the parts that matter. So like you could start here is where the pressure wave is being tracked. And when it gets to the junction here, it now is tracking the pressure waves 3 different directions. And then when it gets to the next device, the next reservoir, the next valve, it starts to move it. So it does track it. It just does it in a simpler form than the differential equations. So all the math is being done at the components, at the surge devices, at the junctions, and at the effective, and it also takes in consideration the effect of friction as well. So one of the things that, when you look at these 2 methods of characteristics and wave characteristics method, one of the things that Bentley talks about in their literature is that, hey, we're picking up more issues than if you just do these 2 things. I've done enough modeling in both softwares to know that you could get the same answer, just add more junctions along this pipe. And we advise to put junctions at every high and low elevation that you have so that you are predicting the pressures correctly. And therefore you can use the software that runs a little bit faster, especially for the larger distribution systems. And that's the benefit to me, that's the benefit as a modeler, is using a software that still gets us the right answer, but does it in less time. So to go from InfoWater to InfoSurge, one, you need the license. But other than that, what happens is you'll get a new tab inside this, inside your run manager, it's Surge. And so the basic setup instructions are in here. You got your duration. You can pick a time. If you have a standard EPS simulation, you can come in here and pick a time that you want to start your surge analysis. So you don't have to do a steady state run. It's really nice because if you have an EPS run, you can find out at what time the highest flow rate is coming out of your pump. And then you just select that time, and it will also use the tank elevations and the other controls out in the system. So you don't have to go set all that up. It's just part of your steady state run. Of course, you can pick the node you want to display when the model is doing its run. Water distribution systems, I recommend the pressure sensitive demand, just because as the pressures change, of course, you're not going to get the same demand out of your faucet or your toilet or whatever's generating that demand. And so that demand will drop off as the pressure drops off. You can set a global wave speed right here, or you can go and do it on individual pipes. Total length, this pipe segment length, I've done some sensitivity analysis with that. For larger systems, I don't go to the smallest pipe length I have. If you have a smaller system, they do recommend that you put your smallest pipe length. So if you have 5 feet, go ahead and make this a 5. For larger systems, this just does more math for you, which is fine, but it also takes a lot longer and doesn't always necessarily give you the getting more accurate results. And I can say that because I've done a lot of calibration to real data. And you can also refine this pipe length through that calibration process. The CV setting here is for your check valve setting. I always leave it 0. You can modify that a little bit if you have a check valve that tends to not stay closed. If you don't have enough back pressure on it, you can modify this to maybe 0.3, 0.5, but I tend to leave it 0. And then you can also allow for cavitation collapse time. Again, I just typically start with a 1 unless I have for some reason I know something else that I need to start changing this to dampen how quickly the cavitation collapse is occurring. A couple other things to convert your InfoWater model to InfoSurge. And these are some things you need to be aware of or to add. Again, wave speeds. There is a tool within InfoSurge that will help you calculate the wave speeds based off of just the material. It'll take in consideration the elasticity and everything about it. And it'll give you a number you can use. Pump inertia, advise you strongly to get that from the manufacturer. However, there is also a tool that will help you figure out pump inertia if you just can't get that information from the manufacturer. We do suggest adding your check valves or your control valves. And to do that, it's the throttle valve in InfoSurge. And you have to have a curve assigned to it. And then you can control it from that point on, either as a check valve or as a control valve. If you have a check valve on the pipe that you have in InfoWater, it will be ignored in InfoSurge. So if you really want to have a check valve in the model, you have to add a throttle control valve and then check off the check valve function in the analysis itself for it to actually behave as a check valve during your simulations. I would suggest putting the pump station elevation details to make sure you're picking up the right pressures. Again, but your air valves are not typically in your InfoWater model. There's no place to put them, but you can for surge. So we're talking about air vacuum valves, we're talking about air combination valves and vacuum breaker valves. The model does not allow air to come out of solution. So air release valves, unless they're 1 inch or larger, don't really affect your system. So I don't generally model air release valves. But these other valves have a vacuum component to them, which will allow the air to come in, and then the software does the orifice calculations and then allows the air to go back out when the pressure returns. Surge relief valves and surge anticipator valves, there's several ways to model them within the modeling software. One is based off timing and the other one is based off of pressure. Surge tanks, you can do closed surge tanks, which would be your compressor style surge tanks. You can do one-way surge tanks. You can do bladder surge tanks. And I think I'm missing one. I think there's another one, but I don't use it very often. But those are available. Again, I strongly suggest if you have a long transmission mains in your distribution system, find the drawings, put in the high, put in the low elevations. So you really understand what's happening in your system. And that's also important if you really want to make sure you're putting your air valves in the right location, that you have this level of detail added to your transmission mains. And one thing we just got reminded about last week in one of our analysis is your pipe lengths need to be greater than 0.5 feet in your model, otherwise it will not run. And that can happen because when we build these all pipe models from GIS, you can end up with really short pipe lengths. So just be aware of that when you transfer to InfoSurge. You do need to be greater than 0.5 feet. The other thing you have to have is no negative pressures to start out with when you want to run surge. I forgot to add that, but it will get a warning message. It will tell you what I just said. If you have any negative pressures to start out with, you can't run transient. You have to resolve those first. So I'm going to go through some case studies. So this is a particular client. They have 1,784 miles of pipe. We have, I think, about 40 to 50% is PVC. So one of the reasons we got involved was they were having a lot of pipe main breaks. And so we were trying to figure out, what was causing some of those issues. They have 1 treatment plant, 26 elevated tanks and or standpipes, and 23 pump stations. The particular area we are looking at, we had done a master plan, and I identified from the master plan that at some point very soon, this particular pump station was going to need to be upgraded to meet the increasing demand of the zone that it was providing. So basically, we were looking at changing the capacity of Hargrave from a 0.6 MGD to a 2.1 MGD pump station. And so that was going to change the velocity pretty significant. So we wanted to do a surge analysis. So this is just a little rendering of how the new pump station was going to look. One of the other things that came along in the master plan was also recommendations for new transmission mains on both the suction and the discharge side. So this is the Hargrave pump station we'll be looking at. This is the tank that provides most of the suction side to it. And this is the tank that we're pumping to on the discharge side. Now, one thing to note is that we are going from a higher pressure zone to a lower pressure zone with this pump station. However, because we're trying to maintain pressures around 40, the losses through the pipe and the demands and such we're not available. Even though this is 940, it's only 30 feet higher than this zone. So we still needed a pump station to get the right pressures. I back up, see a couple times, okay. So we did some field work to calibrate this pump station to give us some confidence in the model, to check our assumptions with the wave speeds and some other behaviors just that you pick up through calibration. So one of the things we noticed in the calibration, once we had stopped the pumps, the pumps at the pump station, we still noticed there was flow going through the pump station. It was about 0.44 mgd. So we added a check valve to our model that opened after the pump stopped to mimic the behavior of water passing through the pump station. And so we were able to kind of use that as a way to mimic what we saw in the field so that we can, work on matching our calibration. Our goal for calibrating to transient, we try to match within 5 PSI. So I'm going to zoom in here. So this is the suction side. So we were started at the tank. The dashed line is the field data, and the solid line is from the model. So we are using tel logs, picking up 1 second increments. And these particular tel logs, at the time we did this, recording 4 times a second, but only reporting out min, max, and average every second. We're doing a normal pump shutdown. We weren't doing a power loss, so we felt like this was reasonable and helping us. So right here at the suction, which is the red, you can see the model is matching exactly, very close to what we were seeing. As we get farther away, the model is a little bit noisier than what was happening, but we're still within our 5 PSI goal. On the discharge side, again, we see that drop in pressure. You can see that the model is picking up that wave that we were also seeing. We're matching the downstream size closer to the tank as well within that 5 PSI goal. So this is with that other pump station on. Again, we want to make sure we understand everything happening. So same thing on the suction side of the pump station, you see the rise in pressure and then the model is also predicting that. Again, the dashed line is the field measurement and the solid is the model. And you can see that we're also matching the discharge side as well with the other pump station on. So this is what we were noticing in the field, was that this flow was moving through the pump station. And that's because of this. During a power loss, the pump will slow down depending on the inertia. That's why the inertia value is really important to understand. But that momentum of water on the suction side, and let me zoom into here a little bit. So the momentum on the suction side is this red. So the water, the momentum still wants to move towards the pumps. And you can see that with the rise of pressure as well. But on the discharge side, the water wants to move away. So when there's enough pressure, and assuming we're the same elevation here, or we can talk about hydraulic grade, when there's enough pressure on the suction side and it's higher than the discharge side, water will want to proceed through the station. Just hydraulically, water wants to go from high to low. And so that's what's happening here. And so part of our recommendation, and you can see that through the flow. So this is to show you the flow. And these are actually images from the software. So this is how the results will look. You can see that it's in seconds and flow. You can also change your flow just the way you normally change it if you want it to be in gallons per minute. But this is the same time period I just showed you the pressure. So you can see we're at 2 mgd, but the flow never wants to stop because the energy is always greater on the suction side than the discharge side. So it always wants to keep flow going through the station. And so what we decided to do was to actually take advantage of that in our design and add a pump station bypass check valve at the pump station, so that the water would go through the check valve, not through the pump. And so the pump can come to a complete shutdown. And then with this new design, you can see that our pressures in the system were all fine. We were above 0. We weren't exceeding any max pressure issues. And that was just fine. So again, our recommendation was to put a bypass check valve. This provided reduction in this pressure fluctuations. We didn't see any unforeseen transient events that could be there in the future. But we did see that water would continue to pass through the station, and we didn't want the pumps just spinning and not having a way to really stop and restart again. So that's why we added the bypass. Case study number 2 is a little bit similar. This is a system that has 1,150 miles of pipe, 4 booster pump stations, 4 ground storage tanks, and 2 interconnections. This is the red zone right here. I just selected this in the domain. This is at the time was a proposed new zone, new growth in this area, but they hadn't yet built the elevated storage tank for this zone. But they have a school in this area here that had a required fire flow. And so this particular pump station, what they were looking at doing was putting in some fire pumps to meet the fire demand. But they were concerned that if the fire pumps lost power during fighting a fire, what was going to happen in their system in this zone. And I'm not going to show you all the results we went through. I'm just kind of show you our final solution. Again, this, I actually have some information here. So again, show boundary valves. This is our tank. Here is the 3,000 gallon per minute fire flow at the school. And this is a high pressure zone or high elevation area. This is also where the area you have greater potential to drop below 0. And of course, we were trying to make sure we're staying above 0 because it's a water distribution system. And these tanks are actually on the suction side of both these pump stations. So they're not in this red zone. But because we do have a tank next to our new proposed fire pump, we use that idea of a bypass check valve again so that we can move water from the 2.5 million gallon tank into the new zone if there was a power loss of the fire pumps. So this is also the imagery that you can get out of InfoSurge. You can color code your minimum, your maximum, and your minimum pressures. So this is the results with that bypass. You can see that this high area here, we are seeing even the max pressure in this area is about 40 PSI. We're not exceeding our goal of I think our goal was, I just had it on the other side. Let me go back real quick. Our goal was 250. So we're definitely not exceeding 250. There's no bright greens. Everything is reasonable pressures. That's another thing too that's really nice is not only are we looking at what's downstream, we can also make sure we're not doing anything upstream with this pump losing power. And the negative pressures, again, this is a high area. You can see that we do have that one area that does drop below 20 at some point in our simulation. Again, we're looking at the minimum pressure over our timestamp. And let me zoom in here. So if I just had a pressure gauge at our pump, I would assume that nothing really was going on in the rest of the system. You know, I'm pumping about 85, I lose power, I drop down, and then I kind of stabilize. But if you were to put a gauge or we're out at that high point, you would see that you were getting below 20 at some point, and it does recover. So we're not too low for too long of a period of time. And given that this is a power loss situation, that is totally reasonable. This is our last case study, and I know I'm talking really fast, so we have about 800 miles of pipe. There was 2 treatment plants and 4 ground storage tanks. So they're not elevated due to the location of this system. So they fill the tanks up through a PSV, and then they pump them back out during peak day demands. This is one of the cases where we actually ran the extended period simulation, found out the max flow was occurring at the treatment plant around 15 hours. And so that way we chose that hour to start our simulation. And then that way we didn't have to go figure out what the booster pump stations or the other tank elevations and what the other pump station was doing. It was going to be whatever it was at hour 15. In this particular case, we modeled one 15 million gallon trim pump and one 40 million gallon high service pump. And we did use the wave speeds. Sometimes, depending on our scope of work, we put and define wave speeds for every pipe material and size. In this particular case, we did that. Sometimes we don't have the scope. We just put a global wave speed, and we are really conservative. We use the higher wave speed for like ductile iron pipe. In this case, we also got the inertia from the manufacturer. They did have a control valve. We did use the other tool that they have in InfoSurge that allows you to generate your curve. given the type of, they have the 4 standard valves you can choose from, or you can put in your own information and generate a curve. They had a surge anticipator valve. They had 2 of them inside the station. So we added that information. And their goal was to stay above 0 and less than 150. So under a power loss of those 2 pumps, you can see here, we're about 53 MGD on one pump. We're doing about 19 on another pump. So given the different inertias and the 2 different control valves, they have 2 different types of control valves. You can see the larger pump, the control valve took about 40 seconds to close. So you can see that there is reverse flow occurring as a control valve is closing through its emergency closure. The other one was more like a check valve. So you can see that it closed pretty quickly and didn't have a lot of reverse flow. So when you're at the pump station itself, this is the surge anticipator valve. We're also showing that. So the flow through the surge anticipator valve, these graphs I exported out of InfoWater and brought into Excel. You can easily do that, which is nice. So obviously when the pump station's operating, there's no flow. And as soon as the pressure got triggered for the surge anticipator valve, which is about 40 PSI, you can start seeing flows also moving out of the surge anticipator valve as the pressures kind of stabilize around 20 PSI inside the pump station. All right, so this is what we want to talk about. So inside the station at the treatment plant, you will notice that, hey, our pressures are staying above 10 PSI, everything's good. However, because we have a full distribution model, we know what's happening out everywhere else. And this section down here is actually dropping way below 0. We're seeing some -13, -14 kind of pressures, a little bit right here. I think it's getting to almost cavitation. So that's out in the distribution system. And that's what the model allowed us to understand what was happening. You can also visualize it again by looking at the max pressures. You can see we're exceeding our pressure goals at some of these locations. This is where that cavitation is collapsing and generating high pressure spikes. You can see here also the minimum pressure. So I kind of wanted to show that a little bit better. So everything that's gray is less than 0 PSI. And this is one treatment plant, and here's our other treatment plant. It was also very interesting. You can also kind of tell where the blending occurs in the system. Because you can tell what effect pump number 1 or treatment plant number 1 has on the system by how it's maintaining its pressures. So it's, obviously it's keeping its pressures fine near the treatment plant, but as it goes farther out, you can see the impact that treatment number 2 has, because now this orange, we're getting below 20 PSI with the power loss. So one of the things too, of course, is elevation. And where we were seeing all those negative pressures is also where they have high elevations. So the red and the orangish color are the higher elevations, and the lighter colors, the blues and stuff, are the lower elevations. So this is the area that they were experiencing, or the model was predicting a lot of the lower pressures was because of that. We did calibrate this model. I'm not getting into those slides. So we did have some confidence that the model was telling us what we were seeing was true. So our recommendation was to do 2 39,000 gallon hydrodynamic tanks. They're going to be air compressor tanks. They were actually just delivered last week. I don't have a current picture of them. They have, this particular client had contract pressure requirements with several of their larger users. So we sized these surge tanks to make sure that we were above 0 pressure for at least 5 minutes, with the idea that they can get the pumps restarted within 5 minutes. Because we have a surge tank, we do always look at a quick closing check valves so that we're not losing the energy back through the check valves, but we're letting the energy go into the system. And we also remove the surge anticipator valves for the same reason. We didn't want them opening under low pressure and losing all that energy that the surge tanks were providing. So this is after the surge tank simulation. We put the surge tanks into the model. You can see here, again, the blue is at the treatment plant and the orange was out in the system. You can see that there's a nice transition. The surge tank puts energy into the system. You can see that very clearly. You can see that also, again, out in the distribution where we had that low pressure that was getting down to -14. Now we're only going down to 14 PSI, and everything's just very smooth and very nice. And that's what a surge tank does. Very useful. So again, the max pressures, no longer are we seeing some of those high pressure issues, because the other thing the surge tank does is also absorbs the return pressure. And now, yes, we are below 20, but we're staying above 0, which was our pressure goal of sizing the surge tanks. And again, that was also, I think, for 5 to 6 minutes, we were trying to maintain pressures. So it is a larger surge tank, but we want to make sure we can get those pumps restarted and provide pressure to the system. So for this, pressure at the treatment plant, losses were fine. However, the complete distribution system revealed that there were negative pressures elsewhere. The surge anticipator cannot provide energy, so it does not eliminate the negative pressures out in the system. And the surge tanks do provide that positive pressure for about 6 minutes is what we size them for. So in conclusion, full distribution system models are important because they do identify issues not just at the station you're looking at, but issues throughout the system. InfoSurge is an efficient tool that allows surge analysis to be performed on existing InfoWater models, ideally calibrated hydraulic models.
Calibrated, yes.
And I down here, I just kind of show you the little icon buttons that will also appear with InfoSurge. InfoSurge, it does require knowledge and understanding about both transients and hydraulic modeling. You do have to add all those lists I gave earlier, the wave speeds, the pump station details, the control valve details, inertia, air valves, anything you have, that information needs to be added to your existing model because it's not in there. And if you can, get field measurements using pressure loggers that can capture instantaneous pressure changes, and so that you can calibrate you can calibrate for surge, not just for hydraulics. Some of the things we change when we calibrate for surge, we'll modify the wave speeds, we'll modify the pump inertia, we'll modify the control valves. We will, there were situations where the client insisted that their air valve was closed, but calibration told us that the air valve was leaking because there was some air coming in that was dampening, because air pockets will dampen your transients. And so you can account for that through modifying your wave speeds if nothing else. So those are some of the things that we use to verify or to build confidence. It's calibration. It just also helps to make sure that the mitigation devices we're recommending are reasonable and cost efficient, because if we don't calibrate the model, the model could be saying much larger issues than it really are there. And so we could be oversizing things, which won't hurt the system, but could just cost the client more money. So if we calibrate, we can give better results and also give the client better costs in the end. I really went through that fast.
Yeah, and that was a tremendous amount of information that you shared with us there, Crystal. And really the key things is that we got an overview of what transients are, right? What is this term, transient, surge, hammer? What does it mean? And why is it important to even analyze it or evaluate it in our water distribution systems? So these are all covered. And then the case studies really highlighted how you approach the modeling without, if any, skeletonization, right? You didn't skeletonize anything. It was a full distribution model where you did the transient analysis. And as you highlighted, a lot of the issues that you were seeing were actually not directly at the pumping station. They were out in the distribution systems in areas that you would have otherwise potentially skeletonized in order to compute it in using a different platform of some sort. So this was a tremendous presentation, and all the case studies really topped it off there. But there are a few questions if we can see.
I'm seeing that right now. You are recording this, correct? So somebody asked for the recording.
Yes.
Yeah. Can the surge start time be set to automatically do surge analysis when the pump shuts down? No, you'd have to run the EPS to find out when the pump is going to shut down and choose that time to start your analysis. It doesn't automatically choose that. You do have to pick a time to do that in. Are you moving these?
Yeah.
Oh, okay. Can a check valve at the pump be yes or no as in hammer without inputting? You still no. Yes. On the pump itself, you can say this pump has a check valve. You do need to give it some timing though. So you can say the check, so whatever kind of check valve you have, you can say it closes, if it's a spring check valve or, 0.1 seconds. If has some dampening device, you can put, 2 seconds, 5 seconds. So you do have to still put a second to it. You can also add some, losses, I believe, still to account for the check valve losses at the pump itself. I only recommend doing that if the check valve is very close to the pump, but a lot of times, we have, the pump may be at one level and there's piping and the check valve's up at a different elevation. So I recommend making sure you put the check valve where it's actually at if it's a significant different distance away from your pump. Because there could be issues that the model will pick up between your pump and your check valve that may, you may need to add an air valve or something in between those. So that will help you with that.
Yeah, and there was another question on the whole thing that we just talked about. It looks as though InfoSurge can run within an unskeletonized model. Is this true?
Yes.
Right.
As long as, again, a couple of things I made note of, you can't have negative pressures. And so what I've seen with some of our models is if you have systems that have a lot of wells, oftentimes we're okay in a hydraulic model knowing it's going to be negative pressure, but you have to change the way your nodes are, either change elevations or whatever, not to change the hydraulics of it, just to get rid of the negative pressures. And where you might have them on the suction side of things because the model won't work. And then like the thing we just talked about, or we found out last week, making sure your pipe distances are greater than 0.5 feet. Otherwise it won't work as well. So those are the two things that limit you. If I have these huge distribution systems that there's a little booster pump station out in the middle of nowhere that's causing me some issues, I'll just deactivate it. But for the most part, I don't have to do anything else. It's nice. You just bring in your current model and start with it.
And then there was a question asking, how do you recommend modeling building pressure tanks? Not sure I completely understand.
Is that like a building pressure tanks? Are you talking about tanks like hot water pressure?
Yeah, we might need clarification on that. So if you can clarify that question, we'll be able to answer it. But then there was another question on recommendations on pipe segment lengths used.
Yeah, I usually start with 10 as my default. Larger systems, it can, again, when I calibrating, especially if I have data that I'm calibrating to that I like and I trust, I can go up to 30, 40. But we've done sensitivity, like we took a model, we played with both the cavitation values and the pipe segments. The larger the pipe segment length you use, the more dampening you will see in your pressure waves. So that's why you want to keep it on the shorter end if you can and have the capability, and the runtime is not a problem for you. But I found 10 to 20 being as high as 30. I don't really do that much higher than that, unless I have data that tells me that that's okay and the system kind of has that dampening effect built into it, and then I'm okay with that. But again, they recommend it to be the largest length or the smallest length you have should be that length segment. But I think that just comes part of transient modeling just comes with experience, I guess. And just, again, having field data is really helpful to guide you in that experience.
Yeah, and speaking of field data, there was a question asking where Were there other instruments used to calibrate your transient model beside pressure loggers?
Not in the ones I showed you. Some of our other data, sometimes we actually measure flow through a Peter rod in addition to pressures, but usually it's just pressures. Sometimes the SCADA may tell us, sometimes we will video the closing of the check valve. So we actually have the video to, because some check valves and control valves, you'll see the arm moving and we can video that. So we actually have that timing. So those are a couple of the other things that we've done.
And then there was a question on how do you address a system which does not have much information on its air valves?
Well, so most water distribution systems don't have a lot of information on their air valves.
Yeah.
A lot of distribution systems don't want to have air valves or maintain them. I usually, because the goal for water systems for me is 0 PSI, so the air valves should never open if you're keeping pressures above 0. So I don't push to put them in there. We do have clients that do rely on air valves as part of their mitigation under a power loss situation. In those situations, you do need to go and actually you can visit the manholes or get their drawings and add that information to that. Because they do help, they will open, they will hold the pressure nearby at least to 0. They're very localized, but I don't get a lot of good information on air valves. The other thing about air valves, I'm not against them. They come into play, they work, whether they're maintained properly all the time. So again, assuming they're not there, you provide yourself a more robust mitigation system than assuming that they're there.
Got it. And then speaking of air valves, there was a question asking, when including ARVs, air relief valves, is that managed via the active network or the physical data set?
All right, so in InfoSurge has one data set. It's called Surge data set. And in that data set will hold your wave speeds, your pump inertia, your control valves, your air valves, your surge relief valves, anything related to surge. There's only one data set. So when it comes to data management, there is a workaround that we have, but it's, let's just say we're encouraging InfoWater to get us data sets. Right now, we just have separate models is how we've figured it out. So here's the thing, because there's only one data set, if you are doing a pump trip and that pump trip will trip in every scenario you have. So you can either use your facility set and deactivate the pump you're not interested in, activate the one you're interested in. If you're trying to do like, hey, I want this pump curve with this inertia versus this pump with this inertia, which one's better for transient? You can still create up scenarios. You just have to do it through the facility manager and not through the data sets. And so the data sets, like the control set, will tell you if the pump's on or off. That does play a role in surge, but the surge icon for the pump will also tell you if the pump's on or off. So if you have the pump off in the pipe in the control set, but in the surge set, you have it as a 1, like, hey, this pump is on, that's going to override the control set. Mm-hmm. So there isn't ability to have data sets yet for surge. So you got to keep that in mind. If you have a model, you're using it. I have a model that I've been using for different pump stations. You have to make sure that you've turned off the other pump trip when you go to trip another pump. Otherwise, they're both going to trip.
And then do you typically place your ARVs at model junctions, at existing model junctions, or how do you approach that?
So usually, okay, so the other thing about InfoSurge, you have to have a dummy node or you have to have 2 nodes connected to your surge element. So if your air valve is at a dead end at a high point, you still have to put another node on the other side of it to put it in the model. I try to put the air valves in the larger distribution system just on an existing junction closest to where the air valve is, unless I'm told that, hey, this air valve is 10 feet off of the pipe because they had to go underneath the road and came up to a manhole, then I might put in that length of pipe to the air valve, but you need to then have a dummy node after that for that air valve to work. You'll get an error message if you don't.
Yeah, and then there was another question on, do you think surge tanks and surge analysis should be performed for all distribution system as part of a best practice? And then there was a comment saying most systems I have evaluated could benefit from them and are under designed for surge. So any thoughts on that?
Yes, I think all water distribution systems should be have a surge analysis performed on them. I mean, again, it's a water system, safety first in my thoughts. In the past, we didn't have the capability of doing full water distribution system modeling, right? So we did the best we could. We looked at the high pressures and we had skeletonized models for a while. We want to protect the people. So I'm a fan of doing surge analysis. Surge tanks are the one thing that provide energy to the system. However, again, up to the client for them to determine, if they want to rely on other methods, which could be, again, I've seen surge anticipator valves work if in some situations. I've seen air valves, enough of them work in certain situations. You just have to get into the model and start playing around and find out what it is.
Mm-hmm. And then there was Jose clarified a question. He said, how do you represent pressure tanks or surge vessels when adding the surge protection devices? Is it exactly how it's designed, or is there modeling tricks
yeah. Okay, so the other things, so if you can get as-built drawings or O&M manuals for your existing compressor tanks or bladder tanks, obviously the ones you probably know mostly is just the volume of the tank, right? What you may not know is how are they operating it the day in and the day out. Especially for compressor tanks, there's like a level range. In the model, you don't put the level range. In the model, you put initial gas volume. And that initial gas volume is usually the ideal level of the compressor tank. I have an Excel sheet that I created where I can mess around with the information they give us and the overall volume and like the levels they tell us from the O&M manual to give me that initial gas volume. So you can set up things like that to help you get the initial gas volume from the O&M manuals. Bladder tanks are a little bit easier because there's usually just a pre-charge pressure. Again, that should be in a spec or in the bladder or in the O&M manual should have that information. If you don't have that information, you have some pressure data, you can mess around with the initial volume to kind of see if you're getting the same pressure from it. We had to do that for a system. But yeah, it is hard. Even surge relief valves, finding out what their initial settings are. A lot of things are just not kept, and you just have to do your best you can to find out. And again, having some kind of pressure data, even if it's their SCADA data, will help you with some of that information.
Mm-hmm. It seems like we have one final question here. It's asking in surge results of a surge node, what does the flow of a node represent? Okay, so if you're talking about air valves, the flow is the air coming into the system and out of the system. So, and you can also do that by switching to volume on the air valve. But when you have flow, if it's a negative flow, that's air coming in. So everything to keep in mind is everything's from the perspective of the pipe. So when you say in, and this goes, I know I'm not answering your question yet. This goes to the resistance factors. When you have a thing that, surge relief valve will have an in R and an out R, same with surge tanks. Whenever the in is related to the pipe, so into the pipe, out of the pipe. So like a surge relief valve, water should never go out of the surge, water should never come from the surge relief valve into the pipe. So you'll have a high RR, high resistance. So the flow is the airflow. Now, what's interesting is that both and the softwares I've seen deal with air, the air can actually become flow in the pipe. So if you click on the pipe near one of your air valves, you might start seeing strange flow values. That flow is not water flow, that is now airflow that is being calculated from the air valve into the pipe. And that usually is right around pumps and air valves is when you start seeing this weird flow stuff happening.
But again, so air valves is a flow. Surge tanks, that flow is actually the liquid coming out of the surge tank. That's the flow. The volume will then be the air at that node. Surge relief valves, the flow. There's usually 3 flow values. I forgot to mention that. You want to look at the external flow when you're at a surge relief valve. That's the flow that's going to come out of the surge relief valve. The in and the out will be exactly the same, just duplicate of each other. That's just the flow going by the valve. It's the external flow, the surge relief valve and the surge anticipator valve that's actually telling you what's going out of the valve. So it gets a little convoluted, but yeah, I hope I answered your question.
Yes, and then there was one more question asking about the use of throttle valves for surge analyses. Can you just reiterate or discuss when that should be done?
Yeah, so in InfoSurge and InfoSurge Pro help manual also walk through some of this. So in InfoWater, you just have one valve, right? And then you have a drop-down list that you can say, is this a pressure reducing valve, sustaining valve, flow control valve, general valve, and then throttle control valve. And I think I'm missing one. So you can have flow control valves, pressure reduced, PRVs, PSVs. You can have those and keep them in your model. But one thing to note is that they will, under steady state, is the value that they will hold the rest of the scenario. So if you have a flow control valve at steady state, it determines 500 going through that. It's going to determine what that orifice calculation is for that 500. And that's the orifice calculation is going to hold the rest of the surge analysis. Same thing with the PRV and PSV. The throttle control valve option is the only one that carries with it the ability to control it under surge. And so when you select the throttle control valve, you need to put a curve in there, put the value at 100, because if you don't put 100, it's going to create huge head loss. And then you can add a check valve component, or you can control it through timing. So there's 2 ways to control a throttle control valve. Either just say, hey, this is a check valve, and the check valve closes in 1 second, 0.5 seconds, 5 seconds. Or, hey, this is a control valve, and now I'm going to describe by time how it's going to move over time. And from fully open, which is 100 is fully open, to 0 being closed. And so that's how you use the throttle control valve.
Mm-hmm. And these are all the questions that we had. And there was a lot of them, so that's great. Good engagement and good activity there. And I think we're going to wrap up here, but if people do send any further questions, we're going to make sure we answer them. You can also feel free to directly reach out to any of us. Our emails are shown on the screen. But before we wrap up, we'd really like to give a huge thanks to Crystal for finding time to give us this water talk and really enlightening us and educating us on this very important topic. And hopefully we can have some more surge discussions in the future. So thank you so much, Crystal, for your time. And thank you everyone for attending, and just have a good rest of your day. Firdaus, I'm seeing Firdaus had raised his hand. There was another question that just came in. Well, it's a thank you. The question that came in is a thank you. So thank you, Crystal, and thank you everyone. And feel free to reach out to us through email.
All right. Thank you guys.
Yep.
Bye.
Bye.